Welcome to part 2 of my Model 1 Sega CD diagnostic and troubleshooting video. In part 1 we kind of went over just the basics of recapping the board, looking for damage traces, discussed continuity testing, and talked a little bit about using a logic probe and a logic analyzer. Last time I didn't have a camera of a tripod, so I wasn't able to actually demonstrate a lot of what I was talking about. This time I do have a tripod, so I'll actually show a couple of things I only talked about in the first video. So this EPROM holds the BIOS that the Sega CD boots from, and even though there is a Sega CD CPU and a Sega CD processing engine here, they don't really access this EPROM directly. Instead, the Genesis CPU communicates through this edge connector, and the Genesis boots off this EPROM just like a game cartridge. And then once the Genesis gets all booted up, then the Genesis starts setting things up with the sub CPU and the sub RAM and the engine to initialize and boot the Sega CD part. So whereas we're seeing a boot failure in part 1, we were able to see that the 68,000 processor on the Genesis was reading garbage code over this edge connector, and so it wasn't booting up properly. And since this EPROM is responsible for feeding code to the Genesis, that's where we're going to focus our efforts. I did verify that this EPROM contains a valid BIOS. I even programmed a fresh EPROM with the code just to make sure that it wasn't a bad EPROM. Still had the same problem. So let's go ahead and step through this. So we've got, starting here, this is address line 0, and we can see that it has continuity. Let's see, hang on. Yep, so anytime these if we get a beep, that means we've got continuity. So let's see, actually A0 starts here at the very bottom, the bottommost pin. And so we can see there we've got continuity, and then the next pin up, and then the next pin up, and so on up the entire address line. So that's where the Genesis reads these lines for setting what data it's going to read off this EPROM. Okay, so we're going to use the logic probe to look at the correct behavior of the EPROM with a logic probe, and then we'll do a little deeper dive, and we're going to do the same with the logic analyzer. So I have a known good Sega CD board hooked up here. You can see it uses a mask ROM, but the pinout is the same as the EPROM that's on my faulty Sega CD board and that Sega used. Just turn it on, you can see the flashing lights, and we've got that, and I can hit reset. And it ejects and the whole 9 yards, so I could actually boot up a game and play it right now if I wanted to. Let me power down, hook up the test clip here. Okay, I'm using a test clip here just to make it easier to probe the points on camera. You can just not use the logic probe and touch the points directly, but the test clip definitely makes it a lot easier. So I've hooked the logic probe up to, I've got the positive lead going off the fusible link right there, and I've got the negative line for the logic probe just hooked up to the corner. It's got a ground rail going around the outer edge of the board. So pretty easy board to hook your logic probe up on. Let me go ahead and turn this on. Alright, and it's booted up. And now let's check our pins. So our first pin here is our voltage, and that shows high, which is what we'd expect. Whoops, just try to eject it. Let's put it back in. Okay, next pin should be enable, and that's showing rapid activity because the chip's getting enabled on and off. That's what we would expect. And then next will be our data lines. Let's see, that's showing activity. That's showing activity. And we'll just keep going down the line here. But yeah, when everything's working right, you should see rapid flickering between highs and lows on your address lines, your data lines, and the memory control lines. You know, the enable line that. Okay, this one's holding low just because it's a ground. Pin 11 on the chip is a ground, so that's no problem there. Back onto more data lines. Activity there. Alright, now we have one more ground. Oh no, let's see. I thought that was a ground. Let's see, it's labeled as G in my diagram here. I'll have to check and see what that is. That's got to be one of the memory control lines. Okay, but as you can see, we're getting activity on all the data lines, we're getting activity on the chip enable, and it's holding high on power and holding low on ground. So that's all correct activity. Alright, so now let's go ahead and probe the right side, and I think we'll see similar behavior. So we've got voltage is holding high. This is a programming pin that the EPROM programmer would use. It's just going to hold high on a Genesis. And let's see, that one shows is not connected in the diagram, but it's reading low. That's okay. And then the rest of these are going to be address lines, so they're going to show flickering activity. Here's A15, A14, A13, A12, A11, A10, A9, and that's another ground. It's going to hold low, that's okay, expect that. And then we're going to have address lines all the way to the bottom. And as we can see, every one of them is showing that rapid flickering between high and low that it should. Okay, so that's the kind of behavior that we look for on a properly running system. It lets you know that circuits are active and addresses are being set, data is being read, and everything is good. So, alright, so now let's see what kind of behavior we get from the bad Sega CD. Let me go ahead and power it on here. And first pin is our power lead, so that's going to always hold high. Second one is chip enable. That would normally be flickering to show activity, but the Sega CD system is pretty much hung at this point, so that's holding high. Then that's data line 15, it's just held low. And we're going to see the same thing for all the other data lines. 14's held low, 13's held low, 12's holding low, 11, 10, 9, 8, and this is our ground right here. That'll always hold low. But we're going to see that pretty much all these other data lines going all the way down to the bottom are just holding low because when the Genesis is reading the programming code, the incorrect programming code, it's crashing, and then all the lines are just going low and the system crashes. Yeah, it's pretty much just low all the way down. And then for the other side, we've got another voltage pin there, that's high. Programming line, that holds low, that's high all the time unless you're programming it with a chip programmer. Then this one shows is not connected in the schematic, but I guess the Sega CD gives it a low signal. Doesn't really much matter in this case. And then next pins are our address lines. And it looks like all our data, while our data lines are all being held high, all our data lines are being held low, all our address lines are being held high. well, maybe not. That one's, let's see, that's A13, it's going low. So some of the address lines are going high, some of them are going low, but the point is there's no activity, and there's no activity because the system's crashed. That's why I had to go to the logic analyzer, because I wasn't learning anything from this, since it wasn't showing any activity. But at least by checking every pin, we can make sure that there's no floating signals where there's not supposed to be. You can see I do get a reading off every pin, so yeah, so every pin's connected, we don't have any floating lines, the chip's getting power, the chip's getting ground, there's just no activity. The logic probe isn't telling us much here except that every pin's connected, so that's when we had to move on to the logic analyzer. Okay, so here I've hooked up the test clip with probe leads for the logic analyzer. Unlike the CPU, when we probed and analyzed the CPU, there wasn't a predefined configuration file. So I had to connect up all the probes manually. I'm going to step through how I configured the, well, how I laid out the configuration on the analyzer so that you guys can reproduce it on similar equipment if need be. So main things to know is I took the 16 leads from pod 1 here and hooked those up to the 16 address lines on the EPROM. And then for pod 2 I did a similar thing, 16 channels, and I hooked those up to the 16 pins for the data lines on the EPROM. And then there's 2 memory control lines on the EPROM. There's a chip enable, which brings the whole EPROM in and out of activation on the circuit. And then there's also output enable, which only gets brought high when the GPU, or sorry, when the CPU wants to actually read the data. So basically the way it works is, as long as you set, the CPU sets an address for the address lines, then when it chip enable and output enable are both held high, that's when the data for that set address is read out from the EPROM on the data lines. So so the 2 control circuits for the chip enable and the output enable are here for pod 3. And so let's go ahead and cut over to the analyzer and I'll show how we map all that out there. Okay, so this is the main boot up screen on the analyzer. First thing is we're going to switch over to the specific logic analyzer expansion card. So there we are. And we can see the little up-down arrows there on A1 and A2. That shows that our address lines and data lines are showing activity. And likewise, the over here on A3, the chip enable and output enable lines are showing activity as well. So this specific analyzer has 2 cards inside of it, so that's why I can assign to have more than one analyzer running at once. In this case, we want to assign this to be all under the same analyzer here. And likewise, over here under type, if we were going to do some troubleshooting on the timing, we'd probably leave this on the timing default setting. We may end up having to come to that depending on what we find with the bad Sega CD, but in this case we're more interested in the state of what's going on, just, you know, the actual, how the address channels are getting set, the data that's getting read out, that sort of thing. We're less concerned about the timing at this point, so I'm going to tell it we want to do a state analysis. And that's pretty much it as far as assigning the pods. So next we'll go to the format. Now this is where we actually say, this is where we assign the lines on each individual pod. So again, we can see the clock is showing a signal here. Oh, for the record, I've got the clock pin connected to the CPU's clock line, because it does need to have a clock in order to, whoops, I didn't mean to trigger that. We do need to have a clock for that the analyzer can, you know, synchronize what the analyzer reads off of what the Sega CD is doing. And so that's our clock channel, is J. Let me scroll this over. Okay, so again we can see that we've got pod 1 showing activity, pod 2 showing activity, and pod 3 showing activity on the first 2 lines. So first thing we're going to do is these asterisks indicate, basically we're assigning a label to whatever asterisks are assigned on this row. In this case, I hooked all 16 channels up on the first pod up to the address lines 0 to 15 on the EPROM. So I'm going to go ahead and, whoops, wrong one. Hang on. Here we go. Modify label, and we're going to say those are the address lines. And I've already got the asterisks assigned 0 to 15 for pod 1, so that's good to go. And then our second one is going to be our data lines. So we'll label that as our data. Whoops. Data. And then those are going to be our second set. There we go. So those are all our 0 to 15, our lines on the second pod. And then finally we're going to have our control lines, C and TR, whoops, control lines, and that's going to be our first 2 bits here, just like that. So now we can see we've got address lines on the first pod, data lines on the second pod, and then our control signals. That's our chip enable and our output enable on the third one. So that's all set. Next, we'll go to triggers. Now, I could just leave the triggers as it is and start getting data. There is a bit more we can do here to make it so that the data we capture is more useful. But let's go ahead and show what happens if we leave the triggers at the default. So I'm just going to go ahead and have it run a cycle, and keep in mind the Sega CD is just sitting on the boot up screen with the planets in the background right now. So if I run that for a second, we can see now it defaults to showing hexadecimal readouts for the address lines, which is what we want, and hexadecimal for the data, which is what we want. For the control lines, it's showing hex. That's not as useful to us. We're going to change that to be decimal. Oh, sorry, not decimal. Binary. And we can see that we're getting some, these cases where it's 0, 1, 0, 1. In this case, the chip enable is on, but the output enable is 0. But what we really care about really are just the cases where it's 1, 1. And we can see that in here, for example, it's setting 1, 1, and then it looks like it's repeating the same pattern twice on here, and that's just because the analyzer reads the data off the Sega CD faster than the Sega CD changes channels. So I won't repeat all the individual steps that I did to reproduce this, but this is an advanced triggering setup that I did to basically simplify the amount of data that was getting captured during the startup process. When the Sega CD is starting up, it reads a long string of address all being held high, with the data all being zeros, for about a full second, just while the Sega CD is, while the Genesis is booting up and everything. And all of that was getting captured, and was a lot of data that we just didn't care about. So I went and set the triggers up to basically ignore all of that to start with, and then capture everything that happened after that. So like I said, I won't show all the steps, but at least you can see what it looks like. So if you end up using the same analyzer, you can recreate the same triggers and do the same thing. So there we go. Okay, now that we've got the configuration all set up, what I want to do is I'm going to do a capture of the good Sega CD's boot up process, and then I'm going to repeat and do a capture of the bad Sega CD's boot up process, and then by comparing the two, that should help shed some insight on what's going wrong. So Go ahead and tell this to capture, and I've got the Sega CD off right now, so it tells us that there's a clock missing. And now when I turn the Sega CD on, we've captured the good boot up process, and you can see that we've got a flurry of instructions here. You can see that I've got the trigger sets that we're only capturing when both these bits are 1. That's when both the chip enable and output enable lines are held high. And then we can see the addresses that are being set and then the data that's being set. So this is a capture from the boot process on the good Sega CD. What we really think we're going to be interested in for comparing to the bad Sega CD is what's going on with the actual signals. So if I switch over to the waveform, this shows the actual activity of each of the address lines as you know, the Sega CD is operating. Let me go ahead and zoom those in a little bit. So you can see over time, we can, as different address lines get held high, you know, that's how it comes up with a hexadecimal address of knowing which memory address to read is based on the zeros and ones that each of these are set to at any given point. So I think what we're going to find on the bad Sega CD is that some of these lines that should be showing activity aren't going to be showing activity, and that's going to be why it's reading bad address. It's setting bad addresses, then reading incorrect code and crashing. Okay, so this is a capture I just took from the faulty Sega CD boot up process. If we go ahead and flip over to the waveforms, I think what we'll see in comparison to the good Sega CD, we're not showing any activity on address 0 and we're not showing any activity on address 3. So right off the bat, that is a big difference in behavior. Actually 0 and so 1's busy, 0 is just holding high, 2 is holding high, 3 is holding high. Let's go ahead and see if that changes at all. Nope, not really. So yeah, there is definitely something wrong with address 0, address 2, address 3 that's causing our problems here. They're holding high, there's got to be a reason for it, but at least this gives us a good clue of where to look next. So what's happening is that these address lines on the EPROM that the Genesis CPU sets on these pins to read addresses are also shared with the Sega CD processing engine. So if I put my continuity tester here on address line 0, from looking at the schematics, it says that the first address line on the Sega CD processing engine is on pin 171. So if we start here, 157 is this corner, 160, 165, 170, go about one pin up. It's hard to do this without magnification. They're tiny pins. There it is. So we've got a continuity between that pin and the address line as well. Maybe. There it is, yeah. With the Genesis. So that's a shared line, it's a shared bus. And that would be the case if I continue on down the line. You know, the second address pin is here on the edge connector, and it's 172 right there. So what's happening then is that there's been a failure inside this custom Sega CD processing engine where it is holding several of those address lines high from when the system is first powered on. And so normally what's supposed to happen is those lines are supposed to be low so the Genesis can do its communication without interference. But when this is forcing these lines to be held high, it's causing the Genesis to set addresses wrong on here, and then it's reading garbage code out. So unfortunately, that pretty much means that this board is not going to be salvageable without replacing this Sega CD custom ASIC. If it was an off-the-shelf part like one of these memory chips or even this Sanyo CD-ROM processor, then we could source another part, but the only way to get another custom Sega CD ASIC is to get one from another Sega CD board that's, you know, died in some other way that we could harvest the part from. So unfortunately, I think this one's going to have to get put on the parts shelf, be a parts donor for another Sega CD repair in the future, or if I have another Sega CD come along that I could harvest that part from, then I can move it over to here, and should probably be able to revive this board because everything else checks out except for that ASIC. So I think that's where this repair ends. This repair didn't work out, but hopefully we'll have more success on the next project. Sometimes you can't save them all, but you can learn a lot along the way about you know, how everything works at a low level, and make sure that, you know, when something's dead, that it really is dead and not salvageable in some other way. So anyway, I hope this video was instructional and useful to you folks, and I'll be back soon with more repair videos. Thanks!